Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is a tetrylen, bicyclic, with a benzene ring fused to a cyclohexane, where C1 carries a CH-PH2 substituent, a diphenylmethyl group, 1H flanked by 2PH, and C2 carries a CH2CH2 or side chain. Moving on to the next step. H+, acid, and heat, delta. Under acidic conditions, the primary alcohol, CH2CH2O, is protonated and can lose water to form a carbocation, or the system can undergo an E1 dehydration pathway. Moving on to the next step. The O on the terminal carbon of the ethyl chain is protonated by H+, generating a good leaving group, water. Loss of water gives a primary carbocation at CH2CH2+, which is unfavorable. However, a 1,2 hydride shift or rearrangement can occur, or more likely the elimination proceeds to give an alkene. And for the final step. Under H+ delta conditions, the alcohol undergoes acid-catalyzed dehydration, E1 or E2. The protonated O leaves as water. The beta hydrogen that is eliminated determines the product alkene. The carbocation, if formed, at the terminal carbon of the side chain would be primary, so a 1,2 hydride shift to give a secondary carbocation at the carbon alpha to the ring, C2 positions substituent carbon, is favorable. Loss of a proton then gives an exocyclic double bond at C2 of the tetrylen ring, C2 is equal to CH, CH3, an endocyclic exocyclic trisubstituted like alkene. The carbocation after water loss and 1,2 hydride shift becomes secondary, benzylic-like at C2 of the ring is actually quite stabilized. The most stable alkene forms by loss of H+ to give the more substituted or more conjugated alkene. Product A shows C1 is equal to C, pH2, with loss of H from C1 and the CH-pH2 becoming is equal to CpH2, and the side chain becoming CH2CH3 after shift. This requires a hydride shift and a ring carbon involvement. Product A specifically shows an exocyclic double bond at C1 with both pH groups on the exocyclic carbon is equal to CpH2 and an ethyl group at C2. This arises from protonation of O, loss of water to give primary carbocation on side chain, 1,2 hydride shift from C2's CH to give carbocation at C2 of ring, secondary, benzylic, then further 1,2 hydride or pH shift or loss of H+ from C1 to give the exocyclic double bond C1 is equal to CpH2 weight, that would require a 1,2 pH shift or H shift from C1. Actually, after 1,2 H shift, cation is at C2 ring, which is secondary. Then loss of H+ from the exocyclic carbon, the CH-PH2 at C1 loses its H, gives C1 C is equal to No. More precisely, cation at C2 ring carbon, loss of H from C1 gives C1 is equal to C2 endocyclic double bond in ring, or 1,2 pH shift from C1's CH-PH2 to the cation at C2 gives a new cation at C1 which is stabilized by the remaining pH, tertiary benzylic, then loss of H from exocyclic position. The most stable carbocation would be at C1 after a 1,2 pH shift, tertiary, stabilized by pH. Loss of H+ from the exocyclic carbon of the side chain carbon adjacent to C2, now is equal to CH, CH3 after shift, gives product, A exocyclic is equal to CpH2 at C1 and ethyl, CH to CH3, at C2. The driving force is formation of the most stable carbocation, tertiary benzylic at C1 after pH migration, and then Zaitsev elimination. Product A has an exocyclic double bond C1 is equal to CpH2 with CHPH2H gone, and the side chain is now CH2CH3 at C2 consistent with a 1,2H shift followed by 1,2pH shift sequence and elimination. B and C retain CHPH2, no pH migration, and show simpler dehydration products. These would be minor products from direct elimination without rearrangement. D involves no elimination and formation of an alcohol product, which is not a dehydration product. The major product under H plus delta favors the most thermodynamically stable alkene via the most stable carbocation intermediate, which is product A. Therefore, the correct answer is A. Therefore, the correct answer is option A.